This video is brought to you by mywayteaching.com.
Measurement of delta U and delta H calorimetry. Okay, we can measure energy changes associated with this is the topic measurement of delta U and delta H. Okay, so here this is the by using calorimetry we can measure energy changes associated with chemical or physical processes by an experimental technique called calorimetry. We can measure energy changes. So from this we can measure energy changes associated with chemical or physical processes by an experimental technique called calorimetry. In calorimetry, the process is carried out in a vessel called calorimeter. So, process is process is carried out in a vessel that is called calorimeter. Okay, which is immersed in a known volume of a liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of calorimeter, it is possible to determine the heat evolved in the process by measuring temperature changes. Measurements are made under two different conditions. Okay, measurement are made under two different conditions, that is at constant volume QV and at constant pressure QP. So first measurement is, so as shown in this is the bomb calorimeter. Okay, the first one is delta U measurement. Okay, for chemical reaction, heat observed at constant volume is measured in a bomb calorimeter. So I will, this is called the whole steel vessel is immersed in a water bath. The whole device is called calorimeter. First, here I am explaining you about delta U measurement. For this delta U measurement, you have to consider this figure. This is called bomb calorimeter. So this is bomb calorimeter. Chemical reaction, heat observed at constant volume is measured in a bomb calorimeter. Here a steel vessel is immersed in a water bath. Steel vessel is immersed in a water bath. Okay, and here a steel vessel is the whole device is called calorimeter. The whole device is called calorimeter, and the steel vessel is immersed in water bath to ensure that no heat is lost to the surroundings. It is ensure that no heat is lost to the surroundings. A combustible substance is burnt in pure dioxygen supplied in the steel bomb, where that is oxygen inlet, that is dioxygen supply. We are supplying, this is the dioxygen supply. Okay, heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Okay, since the bomb calorimeter is sealed, its volume does not change. That is, the energy changes associated with reactions are measured at a constant volume. So during this process, bomb calorimeter is sealed. Its volume does not change. That is, the energy changes. Okay, volume does not change, but energy changes associated with reactions are measured at constant volume. So, under these conditions, no work is done as the reaction is carried out at constant volume in the bomb calorimeter. Okay. Under these conditions, no work is done as the reaction is carried out. Carried out in a carried out at constant volume in the bomb calorimeter. Even for reactions involving gases, there is no work done as delta V is equal to 0. So delta V is equal to 0. If there is a no reactions, even for reactions involving gases, there is no work done. Delta V is equal to 0. No work done. Okay, so temperature change of the calorimeter produced by the completed reaction is then converted to QV by using the known heat capacity of the calorimeter. Okay, next, this is about delta U measurement. Means in this delta U measurement you have to explain the this bomb calorimeter, and then under these conditions no work is done as the reaction is carried out at constant volume in the bomb calorimeter. So when delta V is equal to 0, no work is done. This is about delta U measurement. Then coming to the delta H measurement. So this is the figure calorimeter for measuring the heat changes at constant pressure. Okay, so it is at calorimeter at constant pressure, this figure. Measurement of heat changes at constant pressure can be done in a calorimeter as shown in this figure. We know that uh, we know that delta H is equal to QP. Okay, and therefore heat absorbed or evolved. QP at constant pressure is also called the heat of reaction or enthalpy of reaction. In an exothermic reaction, heat is evolved, okay, and system loses heat to the surroundings. Heat is absorbed, okay. Heat is absorbed and in the heat is evolved and system, sorry, this is wrong. Heat is heat is evolved. The system loses heat to the surroundings, and system heat to the surroundings. Therefore QP will be negative and delta RH will be also be negative. Therefore QP is negative, delta RH is also negative. Similarly, in an endothermic reaction, heat is absorbed. This is in exothermic. Opposite to that exothermic, there is a endothermic reaction. What happens? Heat is evolved here, but here heat is this one, and then it is absorbed, and this one be positive. QP is positive. Delta RH is equal to, this is also positive. Okay, so this is delta H measurement. Next, consider problem. This is 1 gram of graphite is burnt in a bomb calorimeter. Means delta U measurement, what I explained about bomb calorimeter. In excess of oxygen at 298 Kelvin and 1 atmospheric pressure, according to the equation, graphite which is burnt in excess of oxygen at 298 Kelvin at 1 to this which gives carbon dioxide. During the reaction, temperature rises from 298 Kelvin to 299 Kelvin. If the heat capacity of the bomb calorimeter is 20.7 kilojoule per Kelvin, what is the enthalpy change for the above reaction at 298 Kelvin and 1 atmospheric pressure? So this is the question, and I will solve the solution here. Suppose Q is the quantity of heat from the reaction mixture and Cv is the heat capacity of the calorimeter. Then the quantity of heat absorbed by the calorimeter. So quantity of heat absorbed by the calorimeter is equal to Cv into delta T. Okay, where Cv is the heat capacity of the calorimeter. Okay, and Q is the quantity heat absorbed. Okay, so quantity of heat from the reaction will have the same magnitude but opposite sign, because the heat lost by the system is equal to the heat gained by the calorimeter. Quantity of heat from the reaction will have the same magnitude but opposite sign, because the heat lost by the system is equal to the heat gained by the calorimeter. That is Q is equal to minus Cv into delta T is equal to minus 20.7 kilojoule per Kelvin into 299 minus 298 Kelvin is equal to minus 20.7 kilojoule. Okay, here negative sign indicates the exothermic nature of the reaction. This indicates that exothermic reaction. Thus, delta U for the combustion of the 1 gram of graphite is minus 20.7 joule kilojoule per Kelvin. For combustion of 1 mole of graphite, 12.0 gram per mole into 20.7 kilojoule divided by 1 gram per mole. Since delta Ng is equal to 0, delta H is equal to delta U is equal to minus 2.48 into per mole. Okay, so this is the problem. 1 gram of graphite is burnt. First, once again I will read the question. Okay, that is 1 gram of graphite is burnt in a bomb calorimeter in excess of oxygen 298 Kelvin and 1 atmospheric pressure. So this is what equation. So during the reaction, temperature rises from 298 Kelvin to 299 Kelvin if the heat capacity of the bomb calorimeter is 20.7 kilojoule per Kelvin. What is the enthalpy change for the above reaction at 298 Kelvin and 1 atmospheric pressure? Okay, so first you know this equation, Q is equal to Cv into delta T, and after that it will be minus because of exothermic reaction. This is Cv into delta T, and putting the value you are getting minus 20.7 joule per Kelvin. So for combustion of 1 mole of graphite, So what you are obtaining? This is the answer. Okay, delta H.